Hello everyone, today we'll be going over the first 10 problems of the MIT Integration B2022 qualifying round. There's a mix of easy integrals and really interesting ones, so hopefully there's something to delight everyone. Without further ado, let us take a look at the first problem. So this first problem is actually a warm-up problem. If you'd like to give it a go, please feel free to pause the video. Okay, so for the first problem, it turns out that you need to observe that the denominator after being differentiated will give you the numerator. So really the answer to this first problem is simply the ln or natural log of x plus sine x plus c. So that is really all. Don't worry, there'll be more interesting problems. Hopefully you manage to give this problem a go. Okay, let's take a look at problem 2. This is slightly more complicated looking, but actually maybe you like to give it a try. You can pause the video now. Okay, so while the arctan and arc cotangent looks intimidating, actually the key observation is to note that if let's say this is A over B, right, then the arctan of A over B is this angle here, but the arc cotangent of the same A over B is 90 minus this same angle. So what this means is that arctan of x plus arc cotangent of x is always equals to pi over 2. So the answer that we want, the integral, is simply pi over 2. The top is always pi over 2. Integrate 1 to square root 3 of 1 over x dx. Yeah, so really this is just pi over 2 ln x evaluated from 1 to square root 3, and this is pi over 2 ln square root 3, which is pi over 4 ln 3. So that is all to problem 2. Also not too complicated, but you can see the observation needed is getting less and less trivial. So with much anticipation, let's take a look at problem 3. This time there's a really interesting floor x, ceiling x. So if you'd like to give this problem a go, feel free to pause the video. Okay, so for this solution, I think one of the first thing you want to do is investigate this function, floor x, ceiling x. If we just do a very quick sketch of how the thing might look like, I mean, at the integer values of x is quite given. Let's say 0, 1, 2, 3. You know that it will be 1, 4, and 9 at the integer values, right? 1, 4, and 9. What happens in between? Well, between 0 and 1, you round down times round up, right? You will get 0 times 1, so it's 0. Between 1 and 2, you round down times round up, so you get 1 times 2, so you get 2, is 1 times 2 here. Between 2 and 3, you round down times round up, so you get 6. You get 2 times 3 here. And what you want is, you will need to integrate this integral here. But realize that the area under this curve is really just the area of all these blocks of width 1 and height n times n plus 1 if you are starting at n. So it turns out that you can break this integral into 2. So on the one hand, you have integral of, from 0 to 2022 of x squared dx, and this is really just 1/3 x cubed evaluated from 0 to 2022 equals 2022 cubed over 3. Okay, and then on the other hand, you want to evaluate the integral of floor x, ceiling x, and this can be written as the sum from 1 to something that we'll figure out of n times n plus 1. So because if n is 1, you get 1 times 2 as the height. If n is 2, you get 2 times 3 is the height. And what's the endpoint? You have 2021 to 2022, and then the block has height 2021 times 2022, right? So the sum runs from n equals 1 to 2021. Okay, now you need to work out this sum in a way that is computationally efficient. So just to recap at the side here, if you sum squares up to capital N, the formula is 16n n plus 1 2n plus 1. And then if you sum just linear terms is n plus 1 over 2. So with this, you can get the sum here is 16 2021 2022 4043 plus the sum of linear terms is half 2021 2022. So if you want to combine the fraction, you should take out 2021 times 2022 over 6, and then this part is 4043 plus 3 over 6 is half, right? So this thing, so this is 4046, which I can cancel 446 and the denominator, and I get 2023 and 3 here. And the reason why I'm doing this is will be clear in a moment, but for now we have computed the two integrals, so let us put it together. The final answer is 2022 cubed over 3 minus 2021 times 2022 times 2023 over 3. And now you can see why I did put the 3 in the bottom. Now it's really computationally efficient to compute this here. 2022 over 3, taking out the common factor, this is 2022 squared minus 2021 times 2023. And this is 2022 minus 1, this is 2022 plus 1. So using the a square minus b square formula, this thing is 2022 square minus 1 square. So the whole thing in the bracket is 1, and so the answer is just 2022 over 3, which is 674. So a really interesting problem. It tests you the observation of the blocks, but also the computation efficiency that is needed. Okay, so let's take a look at question 4. If you'd like to give it a go, feel free to pause the video. Okay, there are some hyperbolic trigo functions here, but usually for integrals, if you're not very familiar with hyperbolic trigo, you can actually convert it to exponential and work with it directly, work with exponentials directly. So just to recap, push x is ex plus e minus x over 2. And sinh x is ex minus e minus x over 2. So let's park this one side. So the bottom, push x minus sinh x, is the difference of these two. The e to the x cancels and the e to the minus x stacks. So this bottom part is actually literally just e to the minus x, which is really simple. So, and the top part, we can replace with e to the x minus e to the minus x over 2. So this means that the integral we want is simply integral e to the x minus e to the minus x over 2 e to the minus x dx. And so this is the integral of half e to the 2x minus half dx. And this is directly just 1/4 e to the 2x minus half x plus c. So although the hyperbolic makes it look really complicated, if you convert to exponential, it is a standard exponential integration. Okay, so Let's take a look at problem 5. This is where the difficulty really steps up a bit. If you'd like to give it a go, feel free to pause the video. Okay, so what we'll do is, firstly, the square root in the denominator is pretty annoying. So we'll rationalize that by multiplying by the conjugate. So the multiplying by the conjugate is taking the minus version. So this takes a while to write, but the idea is quite clear. So the denominator, we use the a squared minus b squared identity, we get minus 2. So this is half x, and I'll apply the minus to the inside, so we get square root x plus 1 minus square root x minus 1. So what we want to do is to evaluate the two integrals separately. So we want integral half x square root x plus 1 dx. So there's a standard way to think about this. This thing is almost possible to break into powers and to be integrated directly, but the x plus 1 is inside the square root, which makes it really annoying. So naturally what we want to do is we let u equals x plus 1. So this thing becomes square root u, and this one is a polynomial u, which will make it really easy to combine. Specifically, x will be u minus 1 here, and dx is du. So we have this thing is integral half u minus 1 square root u du. So as a specific illustration of what I wanted to say earlier, it is now half u to the 3 over 2 minus half u to the half du, which is really easy to integrate. It's just power. So half 2/5 u 5 over 2 minus half 2/3 u 3 over 2 du. And lastly, sorry, there's no du, I mean plus c, yes. 1 second, so plus c, of course. Okay, and then lastly, substitute back what is u. So this is 1/5. U is x plus 1, so this is x plus 1 5 over 2 minus 1/3 x plus 1 3 over 2 plus c. Okay, and then the other integral can be evaluated similarly, so I will just go through really quickly. This is x minus 1 dx. So I let u equals to x minus 1, and x is u plus 1 du equals dx. So this is integral half x is u plus 1 square root u du. So this is half 2/5 u 5 over 2 plus half 2/3 u 3 over 2 plus c. So this is 1/5, and then I sub back what is u. U is x minus 1 5 over 2 plus 1/3 x minus 1 3 over 2 plus c. Then lastly, we take one minus the other, so the answer is basically, instead of writing the whole thing out, I'll just say is this a, and then I call this b. This a minus b. Then of course plus c. Right, so that's all for this problem. It's a bit tedious, but it has some clear ideas in it. Now let's take a look at problem 6. Now things are really interesting. You have nested cosines here. So if you'd like to give it a go, feel free to pause the video. Okay, for this, let's do some brainstorming. If you look at the cosine function, you have x, and cosine, well, it goes like this from 0 to pi, which is the range of integration. And you might be tempted to think that there's some, I mean, the function is sort of odd around pi over 2, like the odd function behavior. So there could be some cancellation involved if we shift the range from 0 to pi instead to center around 0. And indeed, this gives you the inspiration to try the substitution. Let y equals pi over 2 minus x. So dy equals minus dx. Right, so if we sub in, we get the range is from pi over 2 to minus pi over 2. And then let's see, cosine, and then x is pi over 2 minus y, then plus cosine pi over 2 minus y, and then minus dx, or rather minus dy. So I'm going to use the minus to flip the range of the integral. So now this is from minus pi over 2 to pi over 2, and then I have my dy. Now, cosine of pi over 2 minus y, this is sine y. And then you have pi over, again, cosine pi over 2 minus something. So that is the sine of the thing that you minus. So this is y minus sine y. And now the range is symmetric about 0. Sine is an odd function, so you might think this has a chance of being an odd function. And it did. Let's take a look. What happens? Sine of, if you sub in minus y instead, you get sine of minus y minus sine minus y. This thing is sine of the minus y stays as minus y. The sign here gets negative, so becomes plus sine y. And I can extract out overall minus sign. I get minus sine y minus sine y. So the f of minus y is equals to the minus of fy. So this is an odd function. So an odd function, you integrate from minus pi over 2 to pi over 2, you get 0, because the negative and positive part cancels out. So really interesting question 6 here that uses unconventional observation. Okay, let's take a look at question 7. So if you'd like to give it a go, please feel free to pause the video. Okay, it turns out that problem 7 is a pretty standard integration by part trick. So you see the sine x squared is really nasty to differentiate or integrate or so on, but you can pull out a factor of 2x so that this whole part 2x sine x squared is directly easily integrable. So this is a common trick. Now we use integration by parts, so that means we keep the half x squared, and then we integrate this is minus cosine x squared, and then what you have is minus the differentiated version is x, then minus cosine x squared dx, right? So this is just tidying up over here, and then I have plus the minus cancel, half, and then I put the 2x, so I put a half and a 2 here. So again, that makes it very easily directly integrable. This is sine x squared plus c. So this is the final answer. Yeah, so standard integration by part trick. Hope you enjoy this problem. Now let's take a look at problem 8. If you'd like to give it a go, please feel free to pause the video. Okay, this is a really interesting one. The 1 minus x to the 4 in the bottom looks really nasty. So one of the things you might want to do is common substitution pattern that you see, right? Actually, if you have something like 1 minus x squared in the bottom, you might usually consider substituting something like cosine theta, so that you get sine square instead at the bottom, and then hopefully simplifies with the things on top. It converts the bottom into a single term, which is really nice. But now you have 1 to the x to the 4. So this should give you the idea to try let x equals to square root cosine theta. So that 1 minus x to the 4 is 1 minus cos square, which is sine square. So this gives you dx equals, if you differentiate, right, you have the bring down of power, which is half, and then you have this, the power becomes minus half, and then you differentiate the thing inside, which is minus sine theta d theta. Okay, so now we do the substitution. This is great square root cosine theta. And then what do we have? The bottom, as I mentioned, is 1 minus cos square theta, which will become sine square theta. And then dx is minus sine theta over 2 square root cos theta d theta. Very nicely, the square root cos theta cancels. So you have integral half, and then you have 1 over, actually it's minus 1 over sine theta d theta. Right, because this is sine square, it cancels the sine, so you have 1 copy of sine, the minus 1, then you have the 2. The cosine square root cancel each other. So very neat. Over here, we can directly integrate this. We have integral of minus half. This is cosecant theta d theta, which hopefully you know the formula. The formula is minus ln cosecant plus cotangent plus c. Okay, and of course we need to make the substitution back. So let us take a look. We have half ln, what is cosecant? It is 1 over sine, right? And then what is cotangent? It is cosine over sine. So we have half ln, and this is 1 plus cosine theta, which is x squared, over sine theta. Sine theta is the square root of 1 minus cosine square, so it's 1 minus x to the 4. So this gives you half ln. The bottom can be factorized as 1 plus x squared, 1 minus x squared. So the 1 plus x squared, 1 copy of it cancels out. You get square root of 1 plus x squared over 1 minus x squared. So if you take out the factor of half, you get 1/4 ln 1 plus x squared over 1 minus x squared. So a really interesting substitution problem. Hopefully, you are able to understand why we make this substitution so that we can use this principle in the future. Okay, let's take a look at problem 9. If you'd like to give it a go, please feel free to pause the video. So unfortunately, we have another hyperbolic trigo problem, but this one, there's really not much to it if you know the identity. So this is basically asking for the integral of hyperbolic secant square, right? Now, you may recall that the differential of tangent is secant square. So either you know or you may posit that similarly the derivative of hyperbolic tangent will be related to secant hyperbolic secant square, maybe plus minus or don't know what. So either you already know this identity or you can directly try to differentiate this and then find what it becomes, and you'll realize that yes, indeed it is secant hyperbolic secant square. So really the answer to this is just hyperbolic tangent x plus c. So either you know this identity or you can try and guess from ordinary trigo. So that's all to problem 9. Really short one all of the sudden. Let us take a look at the last problem we covered today. Really interesting. If you'd like to give it a go, feel free to pause the video. Okay, so it looks pretty insane with all the e to the x. But this really suggests to you that you should let y equals e to the x and see what happens. So this gives you integral 0, 1. Okay, wait, before that, so you have dy equals e to the x dx. Right. Okay, so integral not from 0 to 1, but from e to the 0, which is, let's see, let's do that again. So you have integral instead, e to the 0 is 1, and e to the 1 is e. So this is e to the y minus, what is this thing? This thing is e to the x over e to the x. So this is e to the y over y. And then you have this one, e to the x, right, dx. So this is 1 over y dy. Right, because dx is basically dy over e to the x, so it's dy over y. So you have this. So you need to find this integral, e to the y over y minus e to the y over y squared. So it looks like a very nasty integral still. But actually, if we look at this integral, e to the y over y, how might you try to integrate it? You'll use integration by parts, right? I think one of the first things you might try, because e to the y will stay constant. So it's easy to integrate e to the y. So if we integrate this, I keep y over y unchanged, I integrate e to the y, I get e to the y. So from y equals 1 to e minus, now I differentiate 1 over y, I get minus 1 over y squared e to the y dy from 1 to e. I think you might see where this is going. Now firstly, this thing is e to the e over e minus e over 1. So you have this. And this is plus the integral from 1 to e of e to the y over y squared dy. Oh, very nicely, this is equal to the second term over here. So your answer is just to move this term over, and then you have answer is e to the e minus 1 minus e. So very cute problem. So that's all the problems we'll cover today. Let me know in the comment section below which problem out of the 10 is your favorite one. Stay tuned to the channel for more math videos, and see you soon.